So, Josh, you were just telling me, we know various implications when we do operations with complex numbers, right? So, when we multiply complex numbers, what were our implications for that in terms of the moduli and the arguments, you say? Yeah. Yeah. So multiply moduli, or their lengths, and sum arguments. And the marker's running out of ink. Now, in your textbooks, they write it in I want to call it like a fancy way. And you can sort of understand what the notation means. But essentially, it's saying if you have two complex numbers, Z1, Z2, right, what's happening when you multiply them out? Well, if you had your two respective arguments, if you had your two respective moduli, R1 and R2, you're multiplying them. And then what are you doing with the arguments? You're summing them together. So they'll write it out something like this, yeah? But essentially what's happening is, exactly as you said, Josh, it's these two facts. Those are the two facts. You can write out this sort of mathematical terminology here, but I think this gets your message across, right? Division is the same idea. Can you remind me, Tom, what happens when you divide two complex numbers? So instead of multiplying the moduli and adding the arguments, what are we going to do instead? Yep, that's it. So you're going to divide the moduli, and then you're going to subtract the arguments, right? And same idea, you can write that out in the same way. How would you write it out? Well, it would just be something like this, right? If you had Z1 over Z2, that would equal to R1 over R2, R2 D2, cos theta, theta 1, take away theta 2, plus I sine theta 1 minus theta 2. That's how you could write it out formally if you wanted to, okay? All that to say, right, is how do we answer questions related to this now? Well, if I give you two complex numbers, right, so let's take two complex numbers. That's a nice number. Is 2 a nice number? It's not going to be nice, is it? Okay, what we're going to do, we're going to plot two things. We're going to plot Z times W and then Z over W. Okay, two things, slightly different. How are they different? Well, one is multiplication, one is division. Let's plot them on the same axis. Right, so first of all, you want to think about what these look like. You have a modulus of 3, so that's a length of 3. What's the argument of pi and 3 look like? 60 degrees, you got that. So it's going to come out like this. These are not going to be to scale, by the way. So that's going to be a length of 3. That's going to be your Z complex number. This is going to be an argument of pi on 3, right? What would this one look like? It's our W complex number. He's a bit smaller, isn't he? He's got a modulus of 2. And my argument of pi and 6, so it's going to come out to here. Maybe? Something like that. 2, that's my W complex number, okay? And the question is then, all right, I've got two things I'm doing. Z times W and Z divided by W. What are they going to look like in reference to these? And so it's helpful that I've drawn these here already so that you can sort of work with something here, right? You've got these two that you can either use these properties algebraically, you could actually find ZW, but I'm going to ask you to plot these here, or draw what these complex numbers will look like. So what are we thinking?
On W, how much you also see and going straight off.
Good. So if you wanted to write this out, you could write it out algebraically. So you'd multiply these out, so 3 times 2, which is 6, and then cos, what's my angle, did you say? Pi on 2, because you're adding these two together. Pi on 3 plus pi on 6, that's going to be pi on 2, right? And so straight up, vertical, terrible scale, by the way. It should really be up here. So let's say it's up here, like, That here, that would be ZW, right? Z over W, or Z divided by W. What would that look like?
The argument you would minus pi over 6 from pi over 3.
Yeah, and what would that give us?
So we pi over 6.
3 pi on 6. So if you take pi on 3 and take away pi on 6.
Yeah. So we pi on 6.
Pi on 6, good. And my moduli in this case? 3 over 2, you're dividing them. So you can see how it's getting smaller, isn't it? That's cos pi on 6 plus I sine pi on 6, okay? So what that means then is, okay, actually the argument is the same. It's actually at the same place as W in terms of the argument. But what's the difference? The moduli is smaller. So how do you represent that here? Well, because if this moduli is 2, well, we're just going to have to draw it out maybe like this. That's purple as well. Maybe like this. Something slightly smaller. All right, these are not going to be to scale. So that would be Z over W, this red vector that I've constructed. The argument stays the same there, okay? Sorry, it's a bit messy all over here. What I want to show you though is just one last type of question before we go. And it's this one. It's actually from a 2013 HSC paper, right? So have a look at this one. So the question says, hopefully you can read that. It says the Argand diagram shows the complex number Z. So they give you Z there. Notice they don't tell you what's actually happening with Z. They don't tell you exactly what the module is. They don't tell you exactly what the argument is. But what do they give you around it? They give you these coordinates, 1 and 1. Okay, that's your only clue. The question is, which diagram best represents Z squared? Z squared, what's another way to write Z squared? Well, it could be Z times Z, right? That's another way to write Z squared. And we know that when we're multiplying two complex numbers, what are we doing? We're multiplying the moduli, adding the arguments. So what do we suspect should happen to those? Let's start with the argument. What should happen to the argument?
Should increase.
It should increase. Argument should get bigger, okay? That's the first thing. What about the moduli though? What about the moduli?
Moduli will get small.
Why is that?
Because it's the square of the number that's smaller than 1.
Yeah, so for example, 0.5 squared. What's 0.5 squared?
0.25.
0.25. And so it's a unique property with numbers that are less than 1. And you would have looked at this when you look at transformations, like when you take the squares of graph. The behavior when the values are less than 1 mean they actually get smaller. And so that's why you just want to think carefully. The rules are pretty clear, right? But the situations are always going to be different. And so example, in this case over here, when we multiplied them, it got longer and the argument increased. The argument generally will increase unless you've got some positive and negative arguments and things like that, right? But in this situation, what are we certain of? Because we know that the argument is positive here, I'm adding them together, so it should get bigger. That kind of eliminates, yeah, because these arguments, they look like they're kind of saying the same actually, right? So those can go away. Then it leaves between B and D. And so I guess, what's the trap? A lot of people will probably choose B because they think, oh, moduli, we square them so they get bigger, but recognize that this moduli is less than 1 actually. So that leaves you with option D there, okay? That's how they make these problems a little bit trickier. And in 4.04, they have examples of that, different kind of phrasing ones. But we'll look at that on Thursday as well, okay?